Okay, let's get started. I would like to introduce Liyang. Liyang Han currently is a postdoc. Right now is a postdoc at DTU. Liyang received his PhD 2020 in University of Oxford, and then before that, the master's degree from Stanford and bachelor degree from Zhejiang University. In his PhD, Liyang worked on a cooperative game theory for energy applications, mostly for peer-to-peer energy trading. Liyang is very expert in a cooperative game, and he kindly accepted to give a lecture in this course about cooperative game. So thank you so much, Liyang, for accepting the invitation. Thanks a lot. It's our pleasure. And the stage is yours.
Oh, thanks for inviting me to give this lecture. This is actually also the first lecture I've ever given in my life. So bear with me if I make mistakes or stumble along the way. And it was really great to see everybody being so interactive in the past couple of days, and please continue posting questions as we go along. At some point, I might have to prioritize going through the lecture content because it is quite a lot. And since it is the first time it's offered, I would like to, get through it all. So, but still, please post questions. I will try to answer as many of them as possible. And if I can't answer all of them, you can bring them back tomorrow during the exercise session or the Q&A session. So without further ado, let's do our usual recap of what we learned in the previous lecture. I'm just going to give you a little bit of a hint about the few desirable properties of the market clearing mechanisms from the previous lecture. And it would be great if somebody could volunteer themselves to give us a quick definition of all these properties. You can just unmute yourself whenever. Anybody?
Okay, so market efficiency is that the market maximizes the social welfare of all its participants summed together. Incentive compatibility is that the offer prices and bid prices represent the true marginal cost and marginal utility of the participants. Cost recovery means that the market players all have a non-negative profit, that the revenue that they receive covers their costs. And revenue adequacy is the same thing, but for the system operator.
Excellent. No negative profit for participants. Same thing here for operator. Do you mind also, there's a special term, or there's a special occasion in revenue adequacy. Do you remember what that is? Not only that it's a non-negative profit for the operator, it's a more strict, more restrictive.
Saurabh already got that condition. Balanced budget.
Yep. So that's a balanced budget. What does that mean?
It means that it is a non-positive profit for the operator. There's no excess revenue for the market operator.
Yep, exactly. So it's basically a non-negative and non-positive, basically just no revenue at all, or zero revenue for the operator, zero profit for the operator, right? Yeah, okay, so, and can anybody else fill out the table down below? We just went through this table in the exercise session. Anybody else? I guess I'll just go through all the, so for the LMP, is it market efficient?
Yes.
No. Yeah, and for why is it not market efficient is because what the incentive compatibility is also not guaranteed. What about cost recovery and revenue adequacy? Yeah, so both of these terms are correct, are yes. What about VCG that we just talked about? There's only one property that the VCG doesn't satisfy. Which one is that? Exactly, Peter. Thanks. So yeah, thanks for the recap. This is the these are the things that we talked about in the last lecture. And one thing that we didn't mention earlier was this impossibility theorem by Hurwitz, basically that says that you cannot guarantee all 4 market properties altogether, which is why you shouldn't try to find one. So that's so much for the recap. And the objectives of this lecture is to, first I'm gonna review some example of the VCG and to actually implement it on a practical example. And after that, I'm gonna use VCG as a base to introduce the cooperative game theory concept, and alongside that to describe the differences between a cooperative game and a non-cooperative game, especially in terms of their economic properties that we discussed in previous lectures. And thirdly, and finally, I'm going to implement the cooperative game framework also in the energy market clearing process that's very similar to what we talked about before, and also to discuss the properties of different payoff or profit allocation methods within the cooperative framework. So let's bring back the example that Jalal just talked about, the VCG example. I'm reducing the number of generators here to 2 as opposed to 3, just for simplicity. So we have generators G1, G2, and demands D1 and D2. And again, to calculate the VCG payment to G1, there are 2 terms, A and B. And A here is, we actually just went through this, so I'm just gonna go through this really quickly. Since VCG ensures market efficiency, we can just rewrite the 2 terms as A is the maximized welfare of the demands and the generators together, plus the cost of G1, because you do not, when the cost of G1 is included in this, it's a negative term, so it's a minus CG1. So if you want to remove this term again, you have to add the term back into A. And then for B, it is basically the maximized welfare of D1, D2, and G2 together. And then to write this in a more compact format, I'm gonna define a few more things. Here I'm gonna go very slow because this is the first time I'm showing this. Here we have N as a set of players, which is the set of players of a set of all players. And we have N without G1. So this symbol is a set minus symbol. So basically it means that N and take out G1, and you get a set of players with D1, D2, and G2. And now we define V of N as the maximum welfare of everyone in N. And then similarly, V of N without G1 is the maximum welfare of everybody without basically this term. And then again, C with N as a superscript, G1, that means the cost of G1 when it is operating within N, within this, the set of all players. Is that clear? Great. So now we can rewrite A and B in a more compact format. And now we get A as V of n plus the cost of G1 when it's operating n, and B is just the V of n without G1. So the payment becomes this. And remember, the cost of G1 within n is an intrinsic operational cost for G1, which means that if you want to talk about the net profit, remember this is the payment, only the payment from the market operator, to G1. And if you want to talk about the net profit for G1, it actually, you have to remove this term. Then you get actually Vn minus V of n without G1. So this is a very interesting format to represent the net profit of a VCG payment. And we'll definitely use this later in the explanation of the cooperative concept. So now let's do an actual implementation. I'm bringing back the 4-player example. From before, the only thing I've changed is this capacity. Before it was 100 megawatts. I changed it to a different number than this one so that it wouldn't be an exact match, for it to be slightly more interesting. So now we have 2 generators and 2 demands of different capacities, the same offer prices and bid prices as before. Now I would like you to think about how you can calculate the VCG payment to all the players. Just to save time, we're just going to go through the steps of calculating the VCG payment for G1. And later for the exercise, you can go through the whole process and calculate the VCG payment for everybody. And here's a little quick guide. So up here is the VCG payment for G1. And in order to calculate that, you need the maximize the welfare of the set of players with everybody in there. And you also need to maximize the welfare of the set of players without G1. And here I'm using a W term. Before it was written as the cost term. I'm just using a welfare term for kind of what's the word? To represent both the welfare of either the cost of the generator or the utility of a demand. And for the cost, because it's a reversed sign, we have to reverse back. And to compute the maximum social welfare, secondly, with each player missing. So this term, the second step would be this. And then you can just follow these steps to calculate the VCG payment. I hope it's clear. I'm not going to spend too much time on going through this. I'm just going to give you the known parameters and constraints, which is very straightforward as before. If anybody would like to volunteer and go through the calculation together with me, you can just unmute yourself. We're going to try to calculate Vn first, and you can tell me how that is done. Yes, exactly, Barbara. That's the welfare of that is G1 is the negative cost of G1. So how do we calculate Vn, V of n? What is this? This is the maximize the welfare of everyone. I'm going to use Z. What are the variables here? Yeah, exactly. P1, P2, G1, G2 are the variables. And to maximize the social welfare of all the variables together, what's the let's go to the this side first. What's D1's value in the maximized? What's D1's value? Exactly, it's 100. What's D2's value? 50. And why is that? Why do we max out the both D1, D2? That is true. They exactly, thanks, Nora. Because the utility demand, because the offer prices, both offer prices are smaller than both bid prices, and at the same time, the total capacity of the two generators is higher than the total load of the two. So you would basically choose to maximize your loads first, and then go for the generators. So what about G1? What's G1's value in here? Yep, you also max out the G1 value because it has a lower offer price. And then G2 would just fill in the difference, right? So that would be 60. And now you write the maximized welfare as minus 12 times 90 minus 20 times 60, and you add the next, whatever this is. So what about, so now we've calculated this term. What about this term? Do we know this term? Can we calculate this term now, since we're already done the set of players with everybody in there? Yep. We already know. Oh, actually, P star. There we go. We already know that PG1 star is 90, but only if offer price equals the cost of generator. Yeah, exactly. So we're not, let's just assume that we are not considering any market manipulation. We're considering everybody's bidding with their true price. So yes, so now we get, so the welfare of G1 is also can be calculated based on the result of maximizing the welfare of the total the set of all the players. And similarly, you can do this with V of n minus G1. I'm not going to go through that, so just going to give you the results. So V of n equals 3,470, and the welfare of G1 is a minus term, like I mentioned, because the cost is positive. And then, so V of n without G1 is 1,600. And you can just plug all these numbers in this equation, and you will get the VCG payment for G1. And please do that for all the other players after the class, because I need you to compare these values to a different payoff allocation later. And what's interesting here is that this value is only the VCG payment. And what is the profit then? How do we calculate the net profit for G1? Are they the same? Exactly, deduct the cost. So the VCG, so the net profit for G1 would be the VCG payment plus the welfare of G1, which is also minus the cost. So it would, and this cost number is basically this. And this result is the end net profit for G1. So now we've gone through this. I will use this as an example to introduce cooperation. So as we discussed, the V of n and V of n minus G1 is kind of a functional of maximizing the welfare that can be achieved. By here, I define the first definition, which is a coalition. A coalition is basically a set of players that can achieve a maximized objective, a total group objective through some sort of cooperation. So, and the set of players with everybody in there is called the grand coalition. So here, N is the grand coalition, and N without G1 would just be a coalition. And if we consider this market as a cooperation, it can also say it's a cooperative game, then V is the value function of this game, and X is the payoffs, which is also the net profit. So this value, net profit, is the payoffs. Please make sure that you distinguish the payoffs and the payments. The payments is what the market operator pays each player, and the payoffs is the final net profits. And to generalize this game, we define N as the grand coalition again, and I is often used as an index for a player within the grand coalition, and S can be used for any coalition, and it is a subset of the grand coalition. This also includes the grand coalition and also the empty set. First key concept, we already just introduced the value function, and the value function is a very important key concept in the cooperative games. It pretty much is the first step you need to consider when you're structuring a cooperative game. You can define the value function in many ways, but it has to be somehow reflecting your objective. And a very common definition of the value function is the maximized total welfare, like we described in our example. So here, the value function of any coalition S would be the maximized welfare, total welfare of everybody, of every player within S, and everybody's welfare is a function of their own decision variables. And here again, whenever we use the star sign, it means that it's the optimal variable value, so that we can remove the maximum functional here. So yeah, so PI is the decision variable, and the W is the welfare of each player, and when you have the star sign, is the optimal solution to the maximization problem. As a special example, if you plug in the grand coalition N, then this equation becomes the maximization of the total social welfare. And what that means, and if you recall that we just did for our VCG calculation, Vn would just be the maximization of everybody within the grand coalition. And what this means is that we can, again, if we assume everybody is truthful, we can guarantee market efficiency. Because Vn would be the final market outcome. And later I will introduce the concept of payoff allocation, and I can show you that there are ways of structuring the payoff allocation so that cost recovery and revenue adequacy can be guaranteed. But what that means is that we have a Hurwitz impossibility theorem. It means that the incentive compatibility in this case will not be able to be guaranteed, which means that we have to force it in a cooperative game setup. And this force, I say it's forced, it's also you can also consider it as an assumption. If everybody is truthful in this game, then incentive compatibility is a basic assumption. And in practical cases, you can use, for example, penalties and side payments and things like that to ensure that incentive compatibility is achieved, but then you, at the same time, you would introduce externalities into the game. But so that it does get complicated, but again, everybody has limited information about all the other players, and there are cases where you can just assume that everybody can be truthful because they don't know any better. So now we introduce the differences between a non-cooperative game and a cooperative game. Before, in the previous lectures, we talked about non-cooperative setups, and a common kind of scheme is that you decide what the clearing mechanism is, and you tell everybody what the clearing mechanism is. And then based on that, people use some sort of strategic behavior, and eventually you will achieve some sort of equilibrium. And this equilibrium, in the ideal case, would coincide with the optimization results. But for a cooperative game, it kind of is reversed. So you first optimize the grand coalition, and then you reallocate the welfare achieved through the grand coalition to each player. So the clearing mechanism actually comes after the optimization. And interestingly, VCG is somewhere in between, because before we have VCG as a non-cooperative clearing mechanism, we broadcast that to the players. But because VCG, as we proved in the exercise, is incentive compatible, you can also consider it as a scenario where you first optimize the market, since this is already guaranteed anyways. You first optimize the market and you just decide to use VCG to allocate the payoffs. Although the payoffs here does not guarantee revenue adequacy, which will be different from the majority of the cooperative game allocations that we will be talking about. Is this clear? Do you guys have any questions? Okay. Just post questions if you find this confusing. All right, so let's go back to the very fundamental of the grand coalition, where you maximize everybody's welfare. Again, by using the optimal variable solutions, you can guarantee market efficiency, assuming everybody is truthful. And now we're introducing a second key concept, which is the payoff allocation. And we tend to use X as the payoff allocation symbol. And again, please distinguish payoffs with payments. Payments is what the market operator is giving to the players, and the payoffs is the net profit. And the payoff is a sum of the welfare of a player being in the grand coalition and the payment to this player. And both of these terms can be negative or positive. If you recall what we discussed for the VC for the example before, for a generator, the welfare is negative because it has to pay an operational cost, whereas the payment is positive, and the end result and net profit, which is the payoff, is also positive. And it's the reverse for the demands, because you would like to collect a payment from the demand. So for a demand, this term would, the welfare would be positive because it's a utility, and the payment would be negative because they have to pay for their energy usage. And here we have, we define the set of payoff allocations as an imputation. If it satisfies these two specific criteria, which first one is individual rationality and second one is balanced budget. Individual rationality, as we talked about before, it is basically has the very similar meaning as cost recovery. Here I'm using individual rationality because that's the more commonly used term in cooperative games. Could you explain again the difference between VCG and co-op? Yes, so let me go back to the previous slide. Well, the VCG, I wouldn't say there's a difference between VCG and the co-op. So for a cooperative game setup, you can, because you optimize this total social welfare first and then decide how you allocate the welfare. You can say the VCG is just one of those ways to allocate the welfare to everybody. It just so happens that this way of allocating the welfare is not revenue adequate. And obviously in a real setup, that is not a very good setup because you don't want the market operator to lose money. So in a real cooperative setup, you would try to find a clearing mechanism so that it guarantees both of these. That's why these two should usually be guaranteed so that it's a more rational kind of payoff allocation. Does that make sense? Oh, if you are, okay, great. Yeah, so we use individual rationality here because it is a more commonly used term for payoff allocations. And then a balanced budget, again, that's just a special case for revenue adequacy when the total cost of the total revenue for the market operator is zero. Oh, somebody, two questions. Goran asks question, if I understood you correctly, I would expect that individual rationality would mean that X is greater or equal to 0, the profit payoff is non-negative, not necessarily that it's greater than, or does this make sense? Or could you explain a bit more why? Yes, that's what I'm going to explain next. Before that, let me see what Nima asks. A cooperative game is not necessarily market efficient, right? Unless it is the grand coalition. A cooperative game, if you want to play it, you are basically, the final market outcome should be the grand coalition outcome. And when you want to look at other the smaller coalitions, that is just a way for you to structure how you would like to divide the payoffs. But bear in mind, the grand coalition is what you're looking at. So the grand coalition outcome should be the final outcome. Does that make sense? Notation question for IR versus.
Sorry, it might be clearer to say this one. In equation 1, the individual rationality constraint, you've got that the payment to provider I should be greater than or equal to WI PI at the optimal. So the optimized grand coalition cooperation is N star.
Yep.
What do you mean by set of I star here? Is that across all possible coalitions or the subsets of coalitions, or is that the same as the N?
It's exactly what I'm going to talk about, actually.
Okay, so, sorry.
Do you want to take a guess? So when you put N here, what does that mean?
That's all of the players.
So that's all of the players when I is in the grand coalition, right? So this value would be the optimal operation point of I when it's operating in the grand coalition, right?
Right.
And so similarly for this, that would be the optimal operational point of I when it's by itself. Does that make sense? And
yes, thanks.
And so now, after I explain that, so what is this term? Can anyone take a guess? When somebody's operating on their own, in our specific example, when you have generators and demands, what is the welfare of somebody operating on their own? No, it's not a non-cooperative game. I'm asking you, if somebody is operating on their own, what is their welfare? Meaning that they don't have anybody to yeah, exactly. It's zero. For a generator, it doesn't have any demand. For a demand, it doesn't have any generator to give them energy. So this basically is saying, does that make sense? When I'm saying that somebody's operating on their own, it means that you basically don't have anybody to provide energy or to get energy from. So equivalently, in our specific setup, for individual rationality to stand, it is basically xi is greater or equal to 0. But in some other scenarios, you might have scenarios where an entity can generate a profit on their own. So this is just a more general term. Just specifically in our example, this term equals 0. All right, so for a balanced budget, can somebody explain what these two terms mean separately? Anybody?
Yeah. On the left, we see that the sum of the payoffs of all the players within the Grand Coalition is equal to the term on the right, which is the maximized social welfare of the Grand Coalition.
Yep, exactly. Thank you very much. And like I mentioned before, the purpose of a cooperative game is basically to reallocate the social welfare that's achieved in the Grand Coalition. So this is a representative kind of statement of that. You basically have to somehow give everybody a payoff and sum that up to be able to match the maximized social welfare of the Grand Coalition. And to ensure these two, it means that these two are correspondent with the cost recovery and revenue adequacy. I'm just looking at the chat box. Total value equals total of individuals. Oh, that's just an explanation. Yep. So 0 equals 0. So Sebastian, here, again, X is the payoffs. They're not payments. Remember here, payments is R, and X is the payoffs. So the sum of X is not 0.
Yeah, okay. Okay, no, I get that. But the second statement of mine should be correct, right? Sum of all payments should be 0.
Yeah, exactly. That is a basic definition of balanced budget, which is actually what I'm going to talk about on this page. So this exercise is for you to do after the class. If you can show a mathematical proof why this leads to a balanced budget using the definition that was introduced before, saying when it's a balanced budget when the market operator has neither a financial deficit nor a financial excess. And with that, I think I'm going to give you guys a break. Why don't we convene in 11 minutes? So if you could come back at 5:05, that would be great. And feel free to post questions in the chat box. All right, let's continue. let's go back to the original setup. You can hear me, right? Great. Of a grand coalition and the value function of the grand coalition. Here we introduce a new concept, which is called the marginal contribution of a player. And for a specific player I, as part of a coalition S, the marginal contribution of this player in S is defined as the value of S minus the value of S without I. And you might find this very familiar because we actually just talked about it in the VCG payment. And the VCG payment of a player is basically the marginal contribution of this player in the grand coalition minus the welfare of this player operating in the grand coalition. And to derive to write this in a more general format in any game for a person's VCG payment, it would just be the marginal contribution of this player in the grand coalition minus the welfare. And the payoffs based on VCG would actually just be the marginal contribution of this player in the grand coalition. This was just shown also in the exercise session by Joel. But let's test whether VCG is an imputation. In other words, whether it is a payoff allocation that satisfies individual rationality and a balanced budget. Can you take a guess on whether it is? Is it an imputation or not? Yes or no? We actually already proved this sort of in the exercise before. Is the VCG individually rational? Yes, I see one yes. Yes, it is individually rational, yes. How about is it budget balancing? We haven't proved this, so let's just go through this. No is the correct answer, but let's go through the proofs. How do we prove whether the VCG is individually rational? We proved that the VCG was incentive compatible. Now, how do we prove that VCG is also individually rational? Let's just follow the definition. The VCG payoff is the marginal contribution. And the welfare of I playing by itself is basically the value of I itself as a coalition. And to prove the individual rationality, you basically compare these two terms and you get this, right? What does this mean? What does this term mean? Or this inequality mean? Let me expand this actually to a more general framework. There is a thing called superadditivity for the value function. And it is a more restrictive property of the value function. This is important. This is a property for the value function. Depending on how you define the value function, it can be superadditive or not superadditive, but it is a property for the value function. And the definition of superadditivity is that for any two disjoint coalitions, the sum of the value of these two coalitions has to be smaller or equal to the value that these two coalitions together can create through cooperation. And this is just a special case, right? And to put that into context, let's bring back the example we had before. If we define G1, D1 as coalition S, G2, D2 as coalition T, and G1 and S and T together, the union of S and T obviously is N. And we could just calculate the value of these terms as we did before. And we see that the value of S is this number, value of T is 750. And the value of N is this number. Let's do a check. So if we add up the S and T, it's 3,270, which is smaller than the value of the grand coalition. What does it mean? That means that coalition S and coalition T can create higher values if they actually cooperate together. And so super additivity basically means that for any two disjoint coalitions, they can create a value that is as high, at least as high as the sum of their individual values. And I can tell you that for our game, whatever coalition you have, as long as it is subject to the production limits of generators, to the consumption limits of the demands and the power balance, and note that here we don't have any transmission constraints. There's no line constraints. So I can tell you that this game or this value function is super additive. By player I playing for himself via. So Nima asked, what do you mean by player I playing for himself? Well, I actually talked about this in earlier when we were talking about individual individual rationality. So this term actually is zero, because if a generator is playing by themselves, they don't have any demand to purchase their energy from. So to purchase their energy. So their welfare, it is basically the maximum welfare that an individual player can achieve. And in our game, they can't achieve any welfare if they're just by themselves, right? He is selfish. I'm not sure what you mean by that. Yes. So my question is, can you prove this? I'm gonna give you some time to think about this. Achilles asked, for each disjoint set, we resolve the optimization problem. Yes, so to calculate VS, this would be the maximized welfare for S. Welfare, how do you? So welfare for S, and this would be the maximized welfare for T. I'm gonna give you some time to think about this, and if anybody has any idea how to prove this, you can just unmute yourself and describe your thought process. A hint is to go back to the basic meaning of what this term means. Anybody? Let me ask you a question. When, say, we have coalition S and coalition T, right now they are both independently, I can't spell. Operating. And they get to achieve their maximized welfare. I'm totally abusing all these terms now, but you know what I mean. They get to achieve their individual welfares, maximum welfare. And now I'm asking you, if you now put them together, can they still continue operating the way they did before independently? As in, can they still, is it still a feasible? Why not? Exactly like Goran said, it is feasible, but whether it is optimal or not, we don't know, but at least it is feasible, right? As long as we don't have any transmission line constraints, if you put, you know, if you only have the constraints of the production limits and the consumption limits, and you have two disjoint coalitions, they operate before like what they were, and you just put them together, they could still continue operating the way they were before, right? Which means what? So they can at least achieve, when you put them together, you can at least achieve the profit that they achieved before, right? Is that clear? And if you optimize that, you can only increase the profit or the social welfare. By disjoint, I mean they do not have common players. There's no player in S that's also in T. Does that make sense, John? So Raquel asked, so can we say that the price will not satisfy both coalitions? In which case? I'm not asking about the, so when you put the two coalitions together, how they were operating before, they can at least operate like that, right? That's a feasible solution for both of them. They don't violate any more constraints. And when you optimize on top of that, you can only increase your profit. And is related to horizontal integration or not? Maddie, can you explain what you mean by horizontal integration?
I guess the horizontal integration means that when two players have they play in the same field, so they can be merged. So, or I don't know, they could have a coalition. So since the companies they play in the same field, they do that. Is this the reason why they want to be merged?
There's for no example, reason.
Yes. For example, let's say that we have two retailers. So those retailers, since they do the similar business, or let's say the same business, therefore they have a tendency to be merged.
Okay.
So is this the reason why merging is appealing to them? So it's called horizontal integration.
If appealing can create a higher profit for both of them, it would be appealing, right?
So yes. So what you're saying is that if it's beneficial to them, that you're saying that it's beneficial, then this is the reason why it's appealing to them.
Yes, like as in they can make a higher profit together.
Yes. So
yeah. So okay. I'm right now I'm just asking, if you have two separate coalitions, they don't have any common players among themselves, and they can individually create their own values. And now you put them together, they can at least operate the way they were before, which is the sum of, and you can, as you put them together, you achieve at least the sum of the profits that they already achieved before, or not profits, welfare they achieved before, right? And you only have room to grow if you have, if you can optimize on top of that. So let's just, mathematically, you can just define variable set that takes on the value of the optimal variable values when they're in different coalitions, which means that the PI will take on PI S star if I is in S, and PI will take on T star when I is in T. Since S and T, they're disjoint coalitions, you don't have complicated situations where when I is in both, right? And then this solution set at least satisfies all the constraints in both coalitions, and they would satisfy all the constraints when you put them together, since we don't have any transmission line constraints. Which means that if you plug these back into the equations, you get at least, okay, Vs plus Vt equals this, and this is a feasible solution, but maybe suboptimal, but at least you can increase that by maximizing it, assuming an efficient market. Yes, we have been assuming an efficient market, yes. Is that clear? All right, great. So now we have proved that this is a super additive game and individual rationality, hence, is also proved. Let's look at budget balance. In order to prove the budget balancing property, let's write them out again. So you sum xi over for all the players within n, and you get this equation. Is this equal to Vn? Can you think of a simple, very simple counterexample to disprove this? You can write in the chat or unmute yourself if you have any idea. Using our example, generators and demands. Anyone? Yes, Goran, what's your suggestion?
Hi, can you hear me?
Yes.
Perfect. So if we have one generator and one demand node, if you remove one of them, then the value or the summation on the right will be 0, and then this equality will not hold.
If you remove one of them, the summation on the right, which term do you mean?
The summation of all I. I'd rather point, but it's kind of hard. But the part you underlined, the summation, that part, yeah. Won't
This
that
part?
be 0? Exactly. Won't that be 0 if you remove one player?
Yeah, exactly. If you remove one player, it'll be just basically one player playing by themselves. So this value would be 0, right? And what would be this part?
That would be 2 times, yeah, I don't know what to call that, but you get what I mean.
Exactly. So it will be 2 times V of n, and that cannot equal V of n. So that is a very simple counterexample to, very well, thank you very much, to disprove that this is not a balanced budget. So VCG is not guaranteed to be an imputation. But then the question is, how do we still, but remember the VCG is based on the marginal contribution of a player to the grand coalition, right? And intuitively, it is a pretty good way of defining a payoff, because you're basically defining the payoff based on the contribution of a player. But how do we modify VCG so that it becomes an imputation, but at the same time, it's still based on the marginal contribution of players? Let's write it out again. What are the bits that are inconsistent with the proof we want to achieve. What do you see here? There's an n, and there's this term. What we want is only this, right? So how do we get rid of the n? We can somehow find a coefficient of 1 over n. And for this term, this is only, taking I out of n. What if we continue taking things out of each term and getting the marginal contribution, and so that the terms can cancel out themselves? And notice that this term would be the marginal, this term would be the marginal contribution of another player to the coalition of n without I, and you can continue building that out until it reaches the empty set, which is 0. And if every term here cancels out each other, then this term would become 0, right? So I'm not going to go through the specifics, but I'm going to introduce a very famous payoff allocation, probably the most famous payoff allocation, the Shapley value, which is developed by Lloyd Shapley. And for seminal work, you can refer to the one published in the 50s. And the Shapley value is basically defined as the average marginal contribution of a player to all the coalitions within the grand coalition that contain this player. And remember, the VCG is only the first step. It's only the marginal contribution of a player to the grand coalition, but the Shapley value covers the marginal contribution of a player of every coalition. You can also refer to the second reference. It talks about an alternative expression of the Shapley value that more expresses kind of the marginal contribution aspect, and also the estimation of the Shapley value, which I will also mention again later. But let's look at the Shapley value. We can rewrite this in a more clear format. And here is basically a marginal contribution of I to the coalition S, and for all S within the grand coalition and that contain I. So you do this, and then the Shapley value given superadditivity can be proved to be an imputation. The proof, you can do it yourself. You can follow similar steps as the VCG payment. And if you have questions, feel free to email me or ask me during the Q&A sessions. But I'm not going to go through that proof here as well. And some additional properties of the Shapley value. First of all, the Shapley value is known as the fair payoff allocation, and mainly because of these additional properties. First of all, for symmetry, for all of the coalitions that contain neither I nor J, if the value of adding I and J into this coalition is equal, then you will end up with the same Shapley value for both I and J. And for the dummy player property, if for all, again, all of the coalition that do not contain I, and by adding I in there, you basically only increase the value by the value of I itself. That means that this player is useless in this game, because if you only can increase the value by the value you can create by yourself, then you don't really provide any additional value to the game. That's why it's called a dummy player. And for linearity, this is used very rarely, because you have to have 2 games played at the same time, and both using Shapley value. This is to say that if you are playing 2 games at the same time, both using Shapley value, it's the resulted Shapley value is equal to the sum of the 2 Shapley values if you play the games separately. And if you're interested, you can read the reference to understand more of these fairness properties. But here, let's try an example of a Shapley value. I'm already writing out the values of all the coalitions. So this is only a 3-player game, very simple. So you don't have to calculate values of the coalitions. But let's go through the steps, and also designing all the tables to do this. I need 1 volunteer to go through the steps with me. If anybody can just unmute and follow the steps with me to calculate the marginal contribution and also the Shapley value for each player. Anyone? Just to explain the tables a little bit. So now we listed all the coalitions and the size of the coalitions. And we want to calculate the marginal contribution of player 1 in each of these coalitions. Based on that, then we can calculate Shapley value of the first player. Any volunteer?
Yeah, let's do this together.
All right, cool. So what's in here?
As we said, because we have 1 player, it's 0.
Mm-hmm. And what's the marginal contribution of 1 in 1?
I guess 0.
Why is it 0?
Because he doesn't have any incentive to generate or
so yeah, so the value of player 1 is 0, right? Here.
Which is equal to the marginal contribution.
And why is that?
We showed it earlier because it's the
so what is the marginal? How do you express the marginal contribution of 1 within coalition 1? So it's equal to this minus what, based on this?
Minus minus the value of the disjoint set.
So S here is 1, right? And if you take the player 1 out, what are you left with?
Oh, 2 and 3.
So S is 1, right? Oops,
yes.
1. And if you take 1 out, what is left?
It's the empty set, okay.
It's the empty set, right? So here the empty set is also 0. It's always 0, whatever game you have, right? So it's 0 minus 0, and it's still 0. And what about this one? What about the second column? Does it apply?
I guess not, because the player 1 is not in the set.
Exactly, so it doesn't apply, and similar goes for this one, and the next one.
Well, the next one, the value is, which is the value? Okay, so the value is 0. So it's 0 minus 0 minus doesn't apply, so I guess it's 0 again.
So it's this value minus this value, right? If you take player 1 out, it's left with player 2. Right, and then what's the next one?
So the next one is the value of set 1 and 3, which is 5. Minus taking player 1 out, so minus 0, so 5.
Yeah, so it's this value and this value. And the next one?
I think it's we should put 5 in the table.
5 for the next one?
No, in the.
Oh, sorry. Yeah.
So the next one it doesn't apply. And for the last one, it's 10 minus 9, so it's 1.
Yep. Great. Thank you very much. And how about this? So let's do this calculation. So when S is 1, how many coalitions satisfy this? So these 3, right? Anyone? Let's have another volunteer. Anybody?
Could you repeat the question, please?
Yeah, let's calculate the Shapley value using this equation. We have already calculated the marginal contribution. So basically all these terms. Let's do the final computation of the Shapley value. So we would have to calculate all these coefficients.
So maybe I can help.
Yeah.
So S is cardinality 1, so that's 0 factorial, 1 times n minus s factorial dividing by n factorial is going to be 1 over n. So that's 1 over 3.
1 over 3, so this time 2, same, right?
Yes. Sorry,
yep.
yes. And then
so times what?
Times the sum of what everything we've just seen.
Sum of these, right?
Is
so
the individual ones, which is 0.
Yep, and then the next term?
That's now how do you do 2 minus 1?
Yeah, 2 minus 1 is just 1, right? 1 and times, so n minus, so when s equals 2, this term becomes,
sorry, that's
1 factorial times what's n? N is equal to 3, right?
Yes.
So this would be 1 factorial again, and 3 factorial. Yes. Right? So that would be 6.
And then the sum of the next 3 terms is 5.
So 0 plus 5, right? So 0. And then finally?
And then finally now S is 3. So that's 2 factorial, which is 2 times 0 factorial, which is 1, multiplied by 1.
Yeah, exactly. So now you calculate this. I'm not going to go through the rest of them. So you can calculate the Shapley value for all the players here. And I have a question here. How many coalitions are there for an n-player game? You know how many players are there for a 3-player game? I've already listed all all the possible coalitions. But if you, to generalize this value, how many coalitions, how many possible coalitions are there for an n-player game? Ramen is correct. 2 to the nth minus 1 if you don't count the empty set. But if you include the empty set, it would be 2 to the nth, right? So it is intractable computationally if you increase the number of players. But good news is that, remember, the Shapley values definition is basically the average marginal contribution of a player in a in a coalition. So that means that you can easily just do sampling and try to find the mean value and do a few sampling of coalitions and try to calculate the marginal contribution of this player to those coalitions and get an average to approximate the Shapley value. And this is what this paper is talking about. And there are different sampling methods to get to a better estimate. But this is a pretty basic paper to start with. And now we're coming down to another important topic. I thought I changed this, but apparently not. This should be 9. So notice that if you add the Shapley value of player 2 and player 3, it's 53/6. That is low. That is smaller than 9, which is the value of 2 and 3 together. What does this mean? Anyone?
It's the super additivity property.
Remember the super additivity property is referring to the value function. It's purely a property it's purely a function of the value function. And here the Shapley value is what? It's a payoff allocation. And it has nothing to do, well, it has something to do with the value function, but but the super additivity cannot be applied to a payoff allocation. Okay, I have a few answers. They contribute, Goran says that they contribute more to the game than just their value. And can I repeat the question? So my question is, if you notice that if you add the Shapley values of 2 and 3 together, it's smaller than the value of 2 and 3. I know the confusion here. So when I say Shapley value, the Shapley value is not a value. When I say a value of a game, it is referring to this value. It's usually to maximize the social welfare. But the Shapley value, although it has value in it, it's a payoff allocation. It has nothing to do with the value of the game. So hope that's clear. Sensitivity of the game to removing each player. Sensitivity of the game to removing, not exactly. The payoff for 2 and 3 in the total game is less than their total value in their own game. Yes, and what does that indicate? Upper bound payoff, the payoff allocation is less than their value. Thank you, Raja. Exactly. It means that they will have the tendency to just form their own coalition without participating in the grand coalition to achieve a higher payoff on their own, right? So if I'm saying I'm gonna allocate the two of you these values, when the two of you can actually just operate on your own and achieve a higher value, why would you even participate in this grand coalition? So this is what was referred to earlier. So they're better off actually forming a smaller coalition based on the Shapley value that are given to them. So here is another important definition, which is excess. The excess of a coalition S is defined as the value of this coalition minus the sum of all the payoffs to the players within this coalition. And in this case, the value of 2 and 3, so the excess would be the value of 2 and 3, which is 9, minus the sum of their payoffs, which is 53 over 6. And this equals 1 over 6. So the excess of the coalition 2 and 3 is greater than 0. It is greater than 0, and that means that this coalition is not satisfied. So you can also consider excess as the definition of the dissatisfaction. Of a coalition. The higher the value is, the more dissatisfied this coalition becomes. And in order to make sure that all the coalitions are happy participating in the grand coalition, you have to ensure that a payoff allocation can guarantee that all the excesses are below or equal to 0, which means in that case, this payoff allocation is a stabilizing payoff allocation. Is this clear? Do you guys have any questions? Is it clear?
Just quickly, in the example that you've given, all of the 2-player coalitions are stable and the 3-player coalition is not. Is that correct?
All of the 2-player coalitions are well, this coalition is not stable because it receives a payment that's less than their joint value they can create. The excess of this coalition is greater than 0, so it's not stabilizing. Do I need to explain this again, or are you guys clear on this? Great. And continue on that. So there's a set, the set for a cooperative game, the set of all stabilizing payoffs is called the core of the game. Meaning that if you have stabilizing payoffs and you have multiple of them, you have multiple ways of allocating the payoffs so that all the coalitions are stable. All these payoff allocations are called the core payoffs. So they're all in the core. And we have proved that the Shapley value, in fact, is not in the core because it has as a result of the Shapley value, there are coalitions that are not satisfied, that have an excess that is higher than 0. So the Shapley value is not necessarily in the core in this particular game. But at the same time, the core of a cooperative can be empty, meaning that there are times when you have a game that just does not have a stabilizing payoff. And a very simple example, we have 3 players. Let's just say each player's value is 0 on their own, which is similar to ours. And the value of any 2 players together is 10. and the value of the 3 players together is 21. You can think about this, but there's no way that you can allocate this 21 to the players so that nobody, oh wait, sorry, no, not 21. Not 21, is 11. It is still a super additive game. But you cannot allocate this 11 to the players so that you don't have any coalitions. Say, okay, I'm gonna give, in order to ensure that the allocation for 1 and 3 is higher than or higher or equal to 10, I'm gonna give 1 5 and 3 5. But then 2 is left with 1. Then the coalition of 1 and 2 or 3 and 2 would be would have a deficit, right? So you can think about this later. But this game does not have a payoff allocation that is stabilizing. So does that mean, so John asks, so does that mean that the Great Coalition does not imply the max revenue for all players? It does not mean that. I'm not sure what you mean by does that. What is that? So do you mean if a core is empty? What's the condition? Can you?
Okay, can you hear me?
Yes.
Well, what I mean is that regarding that value of Shapley we obtained, the correlation between 2 and 3 gave them a better value than the great correlation value, no?
No, so here the Shapley value is a payoff allocation that we decided. So basically we're saying player 2 is going to end up with a profit of 19/6 and player 3 is going to end up with a profit of 34/6 based on the Shapley value allocation. But at the same time, if player 2 and player 3 cooperate on their own, they can achieve a total profit of 9, which is higher than the sum of these two, which means that they have an incentive to just operate on their own so that they can allocate their profit in a way that each player, so say you add 1/12 to each player, and then they actually that's the total profit they can achieve. So basically they have the opportunity to achieve a higher profit if they operate on their own. Does that make sense?
Yes.
Great.
But so in that case, they would prefer to work on their own.
Yeah. That's why this is not stable.
Okay.
Yep. So the core can be empty, but my question is there a payoff allocation that is guaranteed to be in the core if the core is non-empty? This is a very complicated sentence. So basically, we're assuming there is a game that has a non-empty core, meaning that there are stabilizing payoff allocations. How do you come up with an allocation? Is there a way to come up with an allocation that is guaranteed to be stabilizing? So Goran asks, what exactly does it mean that they operate on their own? It means that they can form a coalition without being in a grand coalition. It means that these 2 players, for example, have an incentive to defect from the cooperation and only cooperate within themselves. Is that clear? Great. And to answer this question, yes, there is a way, and there is actually another famous imputation that is called the nucleolus that is guaranteed to be in the core if the core is non-empty. The calculation of the nucleolus is even more complicated than the Shapley value. So I'm not going to go into details about the calculation of it. If you are interested, you can read more about it in the following two references. And the second one is actually an application in the energy field. So that's probably more relevant for you and more applied if you want to read that one first. And with that, these are the references that we have introduced in this lecture, and I listed the kind of the topics and the references and summarize them in this way for you to refer to. And there's some key takeaways. We first talked about the VCG being a market clearing mechanism that ensures strategic market equilibrium that also yields and optimizes social welfare. And it can be considered a payoff for the cooperative scheme or a non-cooperative scheme. And when it's considered a cooperative game payoff allocation, you can consider that as the marginal contribution of a player to the grand coalition. And if we assume players are all truthful, a cooperative game first maximizes the social welfare, then reallocate the welfare to the participants. And an important definition is the imputation. Is the imputation that satisfies both individual rationality and a balanced budget. And then we later introduced the Shapley value, which is an imputation of a superadditive cooperative game. Actually, here, I didn't mention this, but a superadditive game definitely guarantees that the Shapley value is an imputation, meaning that it is individually rational and also ensures a balanced budget. But you can actually relax this condition to a monotone cooperative game. It doesn't have to be super additive. There's still some time, so I'm going to wrap this up really quickly. So remember this, is super additivity. For a monotone to apply, to basically you just have the bigger the coalition is, the more value it creates. So as long as the game is monotone, you can actually ensure that the Shapley value is a imputation. It is, yes, and it is calculated by taking the average marginal contribution of a player to a large number of coalitions. And finally, we introduced the concept of a core, which is correspondent to stabilizing payoff allocations that guarantee that all the coalitions are satisfied in the corporation. And the core can be empty, but if the core is not empty, the nucleolus is definitely in the core. So for the exercises, first, same example, please first calculate VCG for all the players, for all. And then I would like you to calculate the Shapley value as well. So here you don't have the value of each coalition anymore. You have to calculate the value and compare the two results. Sorry, I missed some questions earlier. Raja asked, maximizing welfare game is also monotone. Well, monotone is actually more relaxed condition. So if it's super additive, it is definitely monotone, yes. And John asked, non-negative or non-positive? Non-negative.
Yes, sorry, in the previous slide.
Right.
Yeah, there. Sorry, I lost it. Okay, the core of a cooperative game that guaranteed non-negative excesses. But in the previous slide, it was written that stabilizing can guarantee that it's below zero, no?
Oh, wait, did I say? Ah, right. So yeah, good catch. So non-positive.
Okay, that's it. Thank you.
Sorry about that. Thanks. Yeah, so for the exercises, calculate the Shapley value for all the players, and you can compare the two values, the VCG and the Shapley value. Make sure to distinguish between the payoffs and the payments. And now I want you to see if the Shapley value is stabilizing. How do you do that? How do you check if the Shapley value is stabilizing or not? You can write in the chat or unmute. Anybody? Exactly. Check the excesses for all the coalitions, and do that and see if the Shapley value is actually stabilizing. And next, this is more of a programming exercise. After you check that, you can see if the Shapley value is stabilizing. What does that mean? That means this game's core is empty or not empty. If the Shapley value is stabilizing. If the Shapley value is stabilizing, exactly, the core has to be non-empty because there is at least one payoff allocation that is stabilizing, that is in the core. But is there a way to test whether the core is empty or not? So I would like you to follow the following steps to try to compute a different payoff allocation. And well, first, again, you have to calculate the values of the coalitions, and second, I would like you to have to construct a linear program, a program that has the 4 payoffs as the variables, and a fictitious excess that you regard as the highest excess as the 5th variable, the highest excess of all the coalitions. And then write this as a constraint. Well, first of all, you have to write all the constraints for your other payoffs as well. But based on if it's an imputation, you at least have the individual rationality and the balanced budget as the constraints, right? So the constraints would be balanced budget, and individual rationality. And additionally, for the highest excess, how do you write this constraint? You can just, how do you write the highest excess constraint? For time reasons, I'm just gonna give you the answer. Basically, you have to ensure that you have to express all the excesses and make them less or equal to this highest excess. And then you minimize this term. You minimize this term. And you will get a final payoff allocation because the payoff allocation are the variables here. and you get a final payoff allocation, and then you can check whether this value is negative or positive. And if it's negative, what does that mean?
That the core is not empty.
Exactly. So if it's negative, it means that you can have some sort of payoff allocation that ensures the highest excess of the coalition is still negative. Yeah, so actually this is the first step towards computing the nucleolus, but it's only the first step. For the nucleolus, you have to iteratively solve for the highest excess for all the coalitions. So with that, yeah, that is the end of the lecture, and I shall see you guys tomorrow at the exercise session. And I don't know if Jalal has anything else to add. Thank you very much. Maybe Jalal has already.
Oh, okay, I have to mute. Okay, thank you so much, Liyang, for such a wonderful lecture. I really enjoyed.
Thank you.
Just for announcement, tomorrow we will not have a lecture. So the first session will be exercise session of this lecture. So Liyang will be there to run the exercise session. Then the second session will be coffee break. Then, well, it's kind of a social event, just to get to know each other. Also, Rajan created a LinkedIn group. I suppose he's going to share the link with everyone on DTU Inside. So then you can join, we can all join there, and we can be connected through there also. And the last session tomorrow will be for Q&A. Again, Liyang and me both will be there. So if you have any questions so far, not just about lecture 4, about lectures 1 to 4, all of them, you are feel free to, you can ask your questions there. Also, if you have any question about your assignments, the project step 1, again, you can ask. Thank you so much. Since we are, beyond the time, I would like to conclude the session. So tomorrow, whether you have a question about lecture 4, so you can ask there. Thank you so much, and good evening, and see you tomorrow. Ciao.
Bye.